All right. I'm Gunter Zink. I'm a program manager in the SQL Server performance team. I deal a lot with new technologies, especially when there is, when there's performance involved. And we consider SMB from a SQL Server point of view as somewhat of a new technology. So historically, databases are typically run against dash storage. So small SQL servers typically run against a handful of internal drives. When they're larger, they tend to run over SANs from you guys, right? Dedicated, typically, especially our best practices guide, for example, you want to have dedicated LUNs for your SQL servers. You don't want to share LUNs or pools with Exchange or your documents and servers, etc. Now, in the brave new world, we're proposing to run SQL Server over SMB. And there's a number of good reasons for that. It makes management a lot easier. We will go into detail on that. Storage, file server storage is typically somewhat higher available than the local drives that you find in some departmental SQL server that they have under somebody's desk, right? So if you increase availability doing it, you increase performance because typically file servers tend to have more drives than your average departmental SQL server. You reduce the complexity and the cost of running SQL. You don't need someone to babysit and stock spares for those drives, etc. And the operational cost, again, we go into detail on what's involved, let's say, for a reconfiguration on SQL Server running against a SAN versus running against a file server a little later. Now, typically, file servers are used to store Office documents, etc. Right? Volume I/O, the I/O volume is significant, but in terms of gigabytes per I/O or so, it's a lot less than you will see with SQL Server. Typically, when you store your Word document, the whole file gets written just to complete overwrite. It's very common, and typically, file servers run out of capacity before they run out of IOPS on the spindles, right? SQL Server is somewhat different. So the I/O volume ratio is different. The IOPS per gigabyte that you'll see is typically 5 to 20x higher depending on your workloads. Typically 1 to 2 IOPS per gig are common for the busier SQL Server instances, which is quite a bit more than you typically see in a file server. SQL Server, in almost all cases, overwrites in place. We're going to write an 8K page inside a couple of gigabyte database file. We just do small writes that are in place. We're not overwriting the whole thing every time. I have yet to see a SQL performance problem that had good SQL code and not a bad code. That was, you run out of I/O long before you run out of other things in SQL Server. It's very common that your I/O latencies is basically your performance bottleneck. And the I/O is typically not distributed equally. Let's say you have some sales database on your storage. The last week, last month, last quarter is a lot more accessed a lot more frequently than the quarter 5 years ago, right? So there is hotspots, and hotspot is moving. It's not static either. So why would you run this against SMB? Now, historically, in the good old 1 gig Ethernet or 100 megabit, network performance was typically not as reliable as you wanted, and the performance as well. Also, think back a couple of years, typically the file server storage, we used some local RAID card and a handful of drives, so the reliability was less than ideal, let's just say. What has changed? Now, Ethernet has come a long way, and now with 10 gigabit Ethernet being sort of a standard for file servers, and I've seen recent data from HP where basically it looks like more than 30% of the servers are actually ordered with a 10 gigabit option rather than 1 gig. So I'd say 10 gigabit is here to stay, and it's especially for file servers or SQL servers where you need the bandwidth. Speed is comparable with fiber channel. If anything, it's actually slightly faster, right? 10 gig Ethernet has a bit more bandwidth than 8 gig fiber channel. 16 gig fiber channel is not quite there yet. Management of SMB shares is a lot simpler than if you have to deal with a SAN. If you have your SQL server on a SAN, you typically not you not just have just one LUN, you tend to have 4, 5, 10 LUNs, right? And we'll go through what it takes, for example, if you want to move your SQL Server around. And you can keep your database operations in one org. You don't have to go to the sysadmins and to the storage team and, hey, I want to move this. You have to set meetings with 5 people just to move your database from one server to another. And cost, typically a file server tends to be cheaper than a SAN. Now, in your case, you have NAS options for most of your storage arrays, right, which not sure how we factor in the cost here, but okay. RDMA is being the performance guy, I love RDMA, especially the InfiniBand stuff where you have bandwidth that's unheard of. CPU utilization very low. We've seen it actually be lower than the best fiber channel or SAS drivers in some very high bandwidth scenarios. Latency is lower than you can measure with perf1 anyway, which goes only down to 1 millisecond, right? Typically we see single-digit microsecond latencies if we do artificial tests.
So is there a cost comparison between RDMA and NICs and the...
There is one right there.
Oh, perfect.
Okay, let's skip forward to that. So these are that's based on prices I found on the HP website and some other CDW, etc. Those are basically list prices you can get off the internet, right? So 1 gig's typically on board, right? So, and the switchboard is give or take $25. You get 110 megabytes per second typically on a 1 gig link. Boils down to about 23 cents per megabyte per second if you want to do price perf math, right? 10 gig Ethernet, it's usually around $300 per port. The switches are quite a bit more than 1 gig, and so if you're looking at managed switches, it ends up being around $650, $675 per port. Especially when you have to use fiber optic, you need the GBICs on both ends of the fiber, etc. That's factored in here, right? Megabytes, you get about 1,100 megabytes per second. So net, about 90 cents per megabyte per second. 56 gig InfiniBand, which is the FDR flavor of InfiniBand, right? The cards are about $800. The switches are actually quite a bit cheaper than 10 gig. You can get them for about $240 a port. Net about $1,000 per port, and then you look at the bandwidth you can drive over that thing. And so the dollar per megabyte per second is less than 20 cents. So it's actually cheaper than 1 gig Ethernet if you need the bandwidth, right? And on the bottom is 8 gig fiber, which is quite a bit more. And the cards are similar than the InfiniBand cards. They're a little more, but not a lot more. The switchboard is where it gets expensive again, because typically you need to put a $300 GBIC on each end of the fiber, right, and the fiber channel switches as well. So you do the math and it comes to about $2.50 per megabyte per second.
So, but what is the range of InfiniBand? I mean, how?
Yeah, there is length restrictions, and typically, not sure, I think 30 feet is the longest you can go with the copper cables, and then they also have fiber optic options.
Okay.
So if you have a group of racks, that works, but you can't span it across your whole data center. Just here. So this is a step-by-step. What happens if you want to move our SQL server to a bigger server or to a different one, right? We replace the server. We want to keep the database the same. If we have a SAN, we have to take the database down, and then we have to file a request to remap the LUNs, basically meet with the admins, make a plan. When are we going to do it? Which server does it need to be mapped to? What are the worldwide names of the ports we got to map it to, etc. We unmap it, map it to the new one. Quite often there's a SAN switch that needs to be zoned accordingly, so it's a lot of work on that end, right? Then we see the database on the new server, and we do an attach of the database, and that brings it online. On a file share, first thing you want to do is verify that the new server has permissions on the file share, read-write permissions, the account SQL server runs under it has permissions. Then you detach it on the old one and attach it on the new one. Done. It's literally less than a minute to do this. Versus on a SAN, depending on the size of your org and how far organizationally the SAN team and the DBAs and the sysadmins are apart, I've seen this take a week. typically large government environments, it takes a little longer, but it can be done faster. So what have we done in SQL Server to support SMB shares? In SQL Server 2008 R2, we officially started supporting SMB shares, but it required a startup flag in SQL Server to enable SMB support. Basically, UNC path names were enabled using this trace flag. And we started testing SMB as part of our regular testing process for nightly builds, etc. In SQL Server 2012, which we just released, we have now full support for SMB. So if you run your SQL Server as clustered roles, you can actually use SMB shares to put your data on. It gets us around the limitation of drive letters, which was a long-standing limitation in SQL. And we also added support to have the system databases like master, MSDB, tempDB, etc. The ones that SQL needs to start up, those can also be located on SMB share now. And it didn't take very long of SMB testing. We found some interesting performance behavior, and there was a fix that got checked into Windows Server 2008 R2 that significantly increased SMB performance for mixed workloads. Or something where the writes were blocking the reads. Okay, this is why we want to do it, and now I thought I used the chance to talk to you guys about the I/O patterns. SQL does a lot of I/O. What does it do? Why does it do it? And what are the implications? We distinguish between two major SQL Server workloads. One is online transaction processing. Let's say you have a website, where customers can buy and order stuff. That's an online transaction processing workload. The other big workload is data warehousing, where you sift through large amounts of data for business support, etc. So for OLTP workload, most of the I/O will go to the data drives, and you're going to see lots of random 8K I/O. 8K is the internal page size of SQL Server. And so whatever we do on the data drives, we will never do I/O less than 8K. Typically, it's all 8K. The reads are synchronous, meaning the user actually has to wait till the read's complete. And the queue depth that you'll see on your device is driven by the workload. Let's say you have 100 users that all try to look up how many items are in stock, blah, blah, blah. And so each user query, let's say, might have to do 5 I/Os, right? So we have to go find let's say the user wants to know how many bicycles in purple do I have in stock. So the first query looks up what's the product number for the bicycle purple? And then we go to the other table and look what the quantity is for that item ID. So let's say it takes 5 I/O to do that because we have to look up indices and stuff. You have 100 users doing this, you end up having a queue of 500 if they all do it at exactly the same time. So there is no button in SQL Server where we can dial up the queue depth. We can dial it down by reducing the number of active users we allow in SQL Server, but that's not something you want to do. And there's no way to dial up the queue. The writes to the database files are asynchronous, meaning we're not waiting for those to complete. Usually those are background jobs. Let's say one of those 8K pages in memory has changed because the customer bought a bicycle and we just had to decrement the counter for how many we have in stock. So that page has changed. Eventually we have to write that changed page out to disk. That's an asynchronous process. Typically, most customers leave the default settings on, and SQL Server will do a checkpoint every few minutes. Every few minutes it goes through, finds all the pages that have changed, and writes them out to disk. And the way that's done is typically we start issuing writes until the write latency increases beyond 20 milliseconds. Then we start to somewhat back off the intensity at which we schedule writes. So you'll see bursts usually. You see, if you look at a performance trace, you can typically see when the checkpoint started and then when it finished. So it's bursty, but there's some variation. But the latency of those writes is not important. If they take longer, then the checkpoint takes longer. The user won't have any negative performance impact. Usually it's the other way around. For example, if you have a very large write cache in a disk array, those checkpoints will go really quick. But eventually the cache has to destage, and that's when the random read performance gets impacted. And the random reads is what the users are waiting for, basically. Right. And then there's the log drive. The log drive is where we persist every change to the database. Let's say, go back to that scenario where the user buys a purple bicycle. We decrement that counter when he hits submit on his web page. I want to buy it, yes. We decrement the counter. We do a bunch of other things like, charge the shopping cart, add tags, and all that stuff. And before the user gets to the next screen that, yes, you got it now, we basically make sure that all the changes to the database are written to the log file, persistent. So the commit of that transaction is done when the log write of all the changes is done. So latency is key there. Typically, a small write cache works very well because it's small sequential writes. There's very few reads from the log. We only read from the log file if you have to roll back a transaction, which happens, but it's not a common scenario. Again, a little bit of write cache goes a long way, but it is critical that there is no data loss. So, we need to have it mirrored independently, battery backed, etc. The intensity, how much data is written, and also the size of the writes is actually driven by the latency of the storage. We use sort of a circular buffer where we insert data on one end and write one out to the disk. And as soon as that write's done, we basically shift the ring buffer around. So if you see very large log writes, that usually is an indicator that your write latency and the storage is a little high. The write size range is typically, we very rarely write less than 1K, and it won't go over 60K because that's our maximum log buffer size. QDEP will be very low because we don't want to have lots of those in flight in case of a power failure, because that basically everything that's in flight, that data is lost. We can't recover it. Once it's persisted to the log drive, we can recover from it after a power failure. So that's why we keep the Q on the log very, very low. And we always write multiple of the physical sector size. So if you have 5 12-byte drives underneath it, we will write multiples of those. We want to avoid read, modify, writes, because you do the read, you do the modify, and then power goes out, which is lost data. You cannot lose log data. If you have 4K sector size underneath it, we will pad. Let's say we only want to log 800 bytes. If the storage underneath has native 4K sector size, we will actually pad that write with 0, 1 patterns to the full 4K to avoid read, modify, writes on the storage. Now, it's important that if you do that, if you signal 4K sector size, the amount of log space that the customer needs increases by quite a bit. Let's say on your 5 12-byte storage, you have a 10 gig log file, and it's fine. If you go to a 4K storage, that might go up by 30, 40, 50%, or on very lightly loaded systems, it might go up by 4 or 5x. So the space you'll need, because of the padding we do, you'll need a lot more log space all of a sudden when you migrate to 4K storage. Data warehousing. Here it's all about how fast can we ingest the data on disk. SQL will do large sequential reads, 256K, or if it's a dedicated data warehouse system, there's a parameter. We can tell SQL to use large extents, in which case we do 512K reads. We queue an awful lot of I/O there, so the queue might go very, very high briefly. Nothing to be alarmed of as the SAN operator. If there's a queue of a couple of hundred on against a dozen drives, that's okay. What we're trying to do is basically ingest either the whole data file or a certain range of the data files as fast as we can. Typically, it goes faster when you queue more I/O, because then the elevator algorithms on the drives and the arrays can reorder the requests, etc. Bandwidth is key. On the new generation 2-processor servers from Intel with the Sandy Bridge processors, I have a setup where we read 20 gigabytes per second, and CPU is still not maxed. So with SQL, we can ingest a large amount of data. Whatever bandwidth there is, we can make use of it. And the bandwidth is the limiting factor on how long your data warehouse queries run. If you give it more bandwidth, twice the bandwidth, it'll run in half the time, every time. Latency doesn't matter in this case because we basically need to read that chunk of data. We don't really care about the latency of the individual I/O operations that they're doing. The tricky part is to lay out the files so that you're truly sequential on the spindle, because when you do random I/O to a spindle, you get like what, 20, 30 megasecond. You do sequential I/O, you get 150, 180 megasecond. So it's really important that you lay out the data so it's sequential and contiguous on disk. Typically on pooled or thin provision storage, that can be quite tricky to figure out, to keep basically data from what's two LUNs apart once they hit the spindle. So whatever you can do there, get them separated out. Don't share spindles between LUNs, because when you hit the spindle with more than one sequential stream, it sort of turns into random I/O, and you just dropped a lot of performance there. And based on the bandwidth needs, multi-channel, whatever. If you have to use 10 gig, see if you can get multi-channel to work more than one NIC, because 1 gigabyte per second is not even enough to keep an old laptop processor busy during data scan. So you need bandwidth, and that's where InfiniBand comes in really handy. QDR, FDR, InfiniBand. Actually, today, what's on the market? If you have one of those new servers that have PCI Gen 3, and a PCI Gen 3 slot with 8 lanes, which is sort of what most servers have, right, has a PCI bandwidth of about 6.5 gigabytes per second. The only way to get that today is actually put one of those InfiniBand cards in there. If you put in one of those SAS HBAs or fiber channel cards, you're typically limited to 2 or 3 gigaseconds. There's no way you get anywhere near the 6 gigabyte per second without using those InfiniBand cards. That's it. I was hoping for a little more questions.
So for the longest time, SQL Server and Exchange scenarios were not supported in SMB,
right?
Because of the caching at both ends. So what has changed here that makes it possible? Is it like everything is being done right through? What's happening?
Actually, so not everything's being done right through. For log writes, we signal right through, but for data writes we don't. And there is actually a new API, a new buffering flag in Windows Server 2012 that allows buffering on the server but not on the client. But it's not necessarily, I think the buffering wasn't the main reason why. It was mainly around write ordering, things like that, because the log writes, they have to be in order and they have to be atomic and all that. There were lots of problems in the early days of SMB. And to be clear, SQL Server supports SMB 2 as well as 3. So this is not limited to 3. It'll also work, it's fully supported in SMB. It's mostly about the Ethernet stuff. And it's just, lots of problems. Whoever tried it, technically it worked, and we could make it work even 5, 6 years ago on the AutoSQL versions, but lost packets, etc. When SQL Server has one I/O that takes longer, it might actually hold up everything in the system. And so a dropped packet on Ethernet will cause 50, 20x increase for the runtime of the query, because we need an order at some point. So there's just, we tried it every now and then, and it was just not. But now, this time around.
So do you use data center TCP at all? I mean, is it the Ethernet, the IP retries and all that? Was that a problem?
Yes.
Because these days they are using data center TCP to make it all work.
Yes, with TCP, and we're also looking at iWork versus and Rocky for that. And with TCP, yes, there's. But in the 1 gig days, 1 gig by itself is just not enough really to run a SQL Server behind it, right? And the reliability of 1 gig networks, we've seen a lot more dropped packets on older 1 gig networks than you see nowadays on 10 gig. So it works and it's fully supported on 1 gig, but I'd only run really small SQL servers on 1 gig.
Yeah. Yes. Is there also those new features like scale out and cluster failover? Those are kind of requirement?
Right. So fully supported, and it works beautifully. We actually, Klaus and Mitch just got back from a conference in Orlando where we demoed SQL Server running against the clustered file server and failed over under load. The only thing you've seen on the SQL Server query, basically the write query stopped for like 3 seconds, but there was no, you didn't have to restart SQL or reconnect the client. It just keeps running. Works beautifully. Yes.
So, could you talk about smoke testing with non-Windows file servers and some of the, maybe even some more on some perf?
Non-Windows file server. Now, very limited exposure there. Yesterday, we ran on, I don't even know exactly what was behind it, other than it was an EMC SMB server. We had, performance limits based on spindle count and network, but it worked without a hitch. We only had one network interface turned on, I think.
And how could people here go about testing with this?
Testing. Okay, so you have to use SQL Server 2012 to use it.
How do you get a copy?
We have copies on MSDN and everywhere. Eval, you can have the developer version. If you have an MSDN license, the developer version is basically a full-featured version. You can even use SQL Express, which is the free version that's limited to a number of users, limited, the amount of memory is limited, but it also works over SMB. And as workloads, there's some generic workloads you can get, like we have them on our MSDN side, some Northwind, etc. You can talk to your DBAs, they can give you a simple script that loads data or retrieves data. We don't have a prepackaged, hey, let's demo SQL and SMB workload, but there's your DBAs can give you something real quick.
So have you seen any deployments of SQL over SMB out there?
Yes, we have. So we have several customers in production, large customers that use SQL Server 2008 R2.
Okay.
As well as SQL 2012.
I mean, where it gets interesting is where people don't use SAN and they start using SMB. That's where it gets, I mean, do you find that?
We have that, especially in the hosting environment. It's very common.
Oh, really? Okay.
And we expect that to pick up quite a bit now with Windows Server 2012 once it ships, because of their continuous available file server, which is
right.
And we, in general, I expect, that most of what today runs on a departmental SQL Server, 5-year-old 2P box with 3 or 4 hard drives internal, that those will eventually all run against file servers. Similar to when Oracle started supporting NFS, etc. So, for all the little stuff, it's great. But the headache of managing local bias, etc.
Interesting.
All right. Well, thank you.
Thank you.